Alrighty, we're going to continue in Module 7 and go to Lesson 7.1b, which is going to talk about function rules and function notation. Whoa, there's a lot to read here. So I'd like you, if you could read this top part right here, if you want to turn off the video, read that first and maybe highlight some keywords, that would be great. And then when you're done, please start the video. So right now, stop the video. All right, you read the top paragraph. You highlighted some key words here, like input, and we remember that input is the X value. Maybe you highlighted output, and that's the Y value. And then they gave us this mapping, which was really interesting. And I know that we talked about this in lesson 7.1a, that for a function, every X value needs to relate to one specific Y value. The problem with this vending machine, or this example right here, is that when you hit G4, you might get Snickers or you might get Kit Kat, right? So if you are allergic to peanut butter and you get Snickers thinking you were getting a Kit Kat, would you be upset? Heck yeah, you would. So this question here says, what would a mapping look like for a vending machine that is functioning properly, that actually would work correctly? So this one is a sad face. That's not working correctly, right? You hit G4, you don't know what you're going to get back. Okay, so that's definitely not a function. So let's actually create a new mapping. We talked about mappings in lesson 7.1a, that maybe if you hit G4, I don't know, let's actually say that you get Snickers, right? You get what you want. And then maybe if you hit the button G5, right, you get Kit Kat. Now that would be a function, and that would be functioning properly, because for every X value, which is the input, you're given an exact value. You know what you're going to get. Okay, there's no confusion. So let's move down here. When the vending machine is functioning properly, each input corresponds to exactly one output. So maybe I circle that. Input to output, one exactly. The snack that comes out of the machine is dependent on the button you push. We call this variable the dependent variable. Wait a minute, we've already talked about that, dependent variable. The button you push is the independent variable. We've talked about dependent, we've talked about independent. So with some vending machines, companies may stock popular items in multiple, let's say multiple locations. Makes sense. I mean, I like Twix, right? Who doesn't? So this can be represented by the mapping to the right. All right, so let's talk about this one. Does this mapping represent a function? Okay, so you want to ask yourself, input, of course, is X. We just learned that, or we also know that's the independent. Okay, it's not that we just learned it. We knew that. Let me move it up just a little bit. And we know that output, whoa, we're sliding here. Let me go back. We know that output is the Y value, and that's also the dependent. Okay, so we know those two things there. So you got to ask yourself, if you hit E3, do you know exactly what you're going to get? Yeah, you're going to get Twix. There's no confusion. If you hit the button A4, are you guaranteed to get a Twix? Mm-hmm. If you hit D6, will you get a Twix? Absolutely. So there is no confusion. Let me compare that with the one up here. Sorry, I keep going up and down. But remember here, when we hit G4, we're like, what? There's so many options, okay? If an X value relates to two Y values, it is not a function. Think of that as a machine that is broken. Okay, so let's go back here. It says explain why or why not. We're going to say yes. The mapping represents a function. And why does it represent a function? The mapping represents a function because, whoops, I don't know if I spelled because right. Each input, which is the X value, so maybe I put X, relates to one and only one specific output. To one specific output. Okay, that is a vending machine that's working really well, and apparently Twix is really popular. Okay, so let's kind of summarize. What did we learn so far in here? We learned the words independent, dependent. We were reminded about input and output. So let's go back here. We're going to learn two more vocabulary words and a function. I'm right here. The set of input values is defined as the domain. Ooh, a new word. Input is domain. The set of output values is defined as the range. Ooh, okay, so that's new stuff. That's new stuff as well. Domain and range. When the specific input, or X value, is inserted into the function or rule, the output is a function of X. The output is represented as f of X. What? Holy smokes, okay? So we're really kind of digging in deep here. right? We're kind of like not just having a bean and cheese burrito right now. We definitely have a carne asada burrito we're eating here. This is getting pretty intense. So which means the function evaluated at x and is read f of x. Huh? Now it's really easy to think when you have f of x that they're multiplied. We'll talk about that more. This is called function notation. Imagine the input value going into a function machine and coming out a different number, the output value. Something is happening to that number in the function machine. Okay, so I'm sure I read that, you zoned out or probably like muted the video. That's okay, I'm not offended. But I really love these two pictures and I'm a big fan. I think pictures, they just say 1,000 words, right? So here we've got a function rule. Input's going to go in domain, something going to happen to it, and out comes a value or a range. Okay. Or input domain is the same as the x value that goes in, and then what pops out is this f of x. So wondering if you've made this connection, but basically f of x is just another way to write y. Okay. But this is f of x. And I think if I do a couple examples, it'll make more sense. This is not multiplication. So I'm going to say not f times x. Oh man, I just wrote that really small. Okay, so this is not multiplication. Okay, so don't treat it that way. So really the new, that's pretty messy. Oh well. So really this whole blurb had a lot of fabulous stuff. It had domain, it had range, it had this whole thing of f of x, and that's a little weird. Okay, so let's move on to the next page, and I know I can do a better job of explaining it, especially if we use it. Okay, so next page, here we go. Okay, we're almost there. We've got only 3 pages. Hang tight. So we're going to examine the table of values to complete the following. All right, so we're actually on number 1, believe it or not. The first page didn't have any numbers on it, and we've got a table of values. I notice this is really cool that they write input and output. And if you can just remember that output just means the same as y, that would be awesome. Okay. What's 2 other words for input? Yep, it's domain and it's independent. Okay. What are 2 other words for output? Yep, it's the range and it's dependent. Also, don't confuse range here from 7th and 6th grade when you learned that range was like a high number minus a low number, right? With statistics and stuff. So that's different. Range is the y value. All right, what values represent the domain? Sweet, they're the x values. Now, ideally, it'd be nice if we wrote them in order. It's spectacular that they're already written in order. So I'm going to just write -5, -3, 1, 3, and 5. Okay. Also if you notice, I'm writing braces here, so I can write it as a set of numbers. So I'm going to write set of numbers. Use braces. Okay. And then what values represent the range? Well, the range is going to be the y value. So they're going to be right here. And holy smokeroonies, they're also written in order. Awesome. Okay, so that's going to be 15, 17, 21, 23, and 25. And again, I'm going to use braces here. I'm going to represent them as a set of numbers. What function rule represents the table of values? What function rule represents the table of values? Write the rule in function notation. So now we have to actually go back and we're trying to write a rule really in mx plus b. And in order to do that, we're looking at what's happening here. Or maybe what I might see is the fact that when I go from -5 to 15, what am I adding each time? Yeah, I'm adding 20. And to get from -3 to 17, I notice I'm also adding 20. And 20 to get 21. 3 plus 20 is 23, and 5 plus 20 is 25. Okay, so that's interesting. So that wasn't really that hard. If we wanted to, we could actually find the slope as well. Okay, find the slope, I love a good stack and subtract them. But you're probably already seeing that the slope is going to be 1. But let's do it anyway. So we've got our y over x. So that's going to be 15 minus 17, -5 minus -3, -2, smokeroonies. Yep, that's going to be 1. Okay. And then how would you find b? I could insert it here and know that if I went to 0, I would add 20 and I'd get 20. So b would actually be 20. So my equation for this would be, I feel like I want to go right back over here where I first wrote it, if that's okay. The slope would be 1 and the b would be 20. So this would be y equals 1x plus 20, but we're not going to write the 1 there. Okay, now I apologize ahead, but I'm running out of room. So I'm going to go whoop, right over here. Okay, and I'm going to continue with my obnoxious orange line, right? So now I've got y is equal to x plus 20 because I'm not going to write the 1 in front. However, it requested quite nicely for a function rule in function notation. Yes, the F word, I'm saying it. So we want to remember that y is just the same as f of x. So that means instead of having y here, I'm simply going to write it as f of x, and I'm going to write x plus 20. That's actually the rule in function notation, but let me please explain how it works. In this, I don't know, let's call it, I guess, rule, or in this machine, if x is replaced with a -5, if x is a -5, what's -5 plus 20? That's right, it's 15. In this rule, if x is replaced with a -3, what's -3 plus 20? Yeah, it's 17, okay? And honestly, if you want to just kind of go with the idea that y can just be written as f of x, that's okay. But that is what function notation is. Remember, this is not f times x. It's a really common error, so please don't make that. This is not f times x, okay? All right, so we're going to move this up, and we're going to try number 2 and number 3. All right, direction. Use the words input and output to describe the function rule for each of the following relations. Write the function rule as an equation, all right, but using function notation. So again, that's telling me it's going to be f times x. If the relation is not a function, explain why. Ooh, kind of tricky. Okay, so first of all, let's examine and see if this is not even a function. Okay, to not be a function, that means the x values would repeat. If I put 1 into the machine, I know what I'm getting. I put -4. Yep, it's looking good. I don't have any x values repeating, so I already know this is a function. So I'm going to write function with the smiley face, okay? Remember that f of x is just the same as y. That's all it means. So let's see if we can figure this out. I don't know. Can it be as easy as if I add 3, I get 4, I add 3, oh, no, that's not going to work. So maybe I have to start with the function rule. And I'm thinking my goal is to get mx plus b. So now I'm going to go back again, and I need to figure out probably my slope might be a good thing to do. So I'm going to find slope, because slope, of course, we're just going to use our 2 points, any 2 points you want. And should we sing the song? Because we stack them, subtract them, y over x, you know. Nah, I guess not. Not as much fun. But we stack them, subtract them. So 4 minus -11, 1 minus -4. When I do this, I get 15. When I get here, I get 5. Woohoo! My slope is 3. Awesome. Okay. So I'm almost thinking that would mean if I want x to be 0, if I can squeeze it in there, I'm going to squeeze it in there. Then for every 1 point I go back 3 points here. So actually, I think that would be 1. That's probably your easiest way to find the b value. Of course, you could always solve for b, which what we've done in Module 3. But remember, if I'm moving up, if the slope is 3, then that's the same thing as 3 over 1, rise over run. All right, so then my function rule is actually y is equal to, the slope is 3, and we found the b value to be 1. But is that written in function notation? To be in function notation, the y value needs to be rewritten as f of x. Okay, and remember that is not f times x. Remember that's not going to be f times x. That's going to be, if x is a 1, then 3 times 1 plus 1 will give you the output, which would be 4. Okay, so be careful, that's not multiplication. So I probably did this problem a little bit backwards, but we're going to just describe this function using the words, I think it said input and output. So it looks like if we're adding 1 and we multiply the input by 3, it gives you an output. Okay, so think about this as a machine. You're putting something into the machine, and the machine's going and going and going, and it spits this output. Okay, so we take the x value, we multiply by 3, we're going to add 1 to it, and that will always give us this corresponding output or y value. Okay, so we multiply, we'll write that down here, multiply input value by 3, add 1 to the product. Ooh, I'm getting fancy. Then you get the corresponding output value. Ooh, that was pretty fancy. Okay. So let's try this again. Let's move on to number 3. I'm going to move it up just a little bit. Hang tight. We just got one more page. You're just learning function notation. Crazy. So as I look at this one, and remember output, f of x is y, and this is input, let's first determine if this is even a function. So if I have the x value of 2, do I guarantee to know for sure what y value I will get? So if I put 2 into my vending machine, let's say, am I guaranteed to get what I want? Well, if I put 2 in, it looks like I'm going to get a 3. Whoa, but I put a 2 in here, I might get a 7? I mean, think about the bouncy ball scenario, right? And if I put a 2 in, I might get squat. Dang, I'm not that happy. Okay. So the x value of 2 does not relate to one specific output value. This thing is not a function, so I can't even write a rule. So not a function. Okay. And I'm going to write the reason why. For the input value of 2, there are multiple, there's 3 of them actually, there are multiple output values. So again, if we think about the vending machine, we're going to be pretty ticked off, right? If I wanted a Twix and I hit the number 2, I might get Twix, I might get that Snickers, or I might get that Kit Kat, right? Now, if you like chocolate, you're happy with any of it, right? But this would be a broken vending machine. This would not be a function, okay? All right, we're turning the page. We've got the very last one. Here we go. All right, let's examine one more scenario, one more table of values, okay? First of all, we need to determine if this is even a function. So again, I'm looking at my x values. I do notice that none of them repeat, which is awesome. So again, if I put in a -2, I'm guaranteed to get a -8, and so on and so on. So this is cool. So it's definitely a function. So I'm going to write function with the smiley face. Okay. But let's see if we can figure out the rule, because I'll let you in on a little secret. This is not linear. Okay. So it looks like in this case, like I'm seeing 3 and I see 27. I'm looking at 5 and 125, 4 and 64. And we just talked about the cubed root, hint, hints, would undo something that is cubed, hint, hint. So it's not a coincidence that if you take -2 to the third power, you get -8. And if you take 3 to the third power, you get 27. What? And it actually works for all of them. So you might be like, what, Miss Griffin, how did you figure that out? Well, I have the answer key in front of me. That always helps. Ha, ha, ha. But you've got to do a little brain power there, that your brains are awesome. You're looking at it. You're trying to come up with a pattern. This one's definitely different. It's not linear at all. So the function rule in this case would be, remember this is y and this is the same as x, that for every y, to get the y corresponding y value, you take the x value and take it to the third, right? -2 to the third power, 3 to the third power, and so on. But that's not in function notation. So you need to rewrite it as f of x equals x to the third. How would we describe this? We're going to say that the input value, value, which is x, is cubed to find the corresponding output value. Okay, that's kind of cool. So remember, even though it's not linear and it doesn't make a line, it can still be a function. Okay, so are all functions linear? Wait a minute, I think I just gave that away. Are all functions linear? Absolutely not. Okay, we have an example right here. Okay. Gosh, I had a thought and then I sidetracked. But are all functions linear? No. Okay. Functions can like f of x equals x to the third. What about a parabola? We've talked about that a little bit. I think on the previous, there was some graphs that were in this shape right here as a parabola. So it doesn't necessarily have to be linear. But the question is, are all linear equations functions? And in fact, I might bust out the infamous purple pen and sidetrack here and do like a 5.5 question and say, are all linear equations functions? And what are you going to say to that? No. Okay, because which linear equation is not a function? That's right, it's a vertical line. Okay, so don't automatically assume because it's linear, it's a function. It's that vertical line that doesn't work. Don't automatically assume that if it's a function, are all functions linear? No way. Okay, so let's actually apply this function rule and get into some computation a little bit here. Given the function, right, this guy here, and remember f of x is just, I'm going to move back to my blue, although the purple and the blue kind of look the same anyway, so there's not much of a difference. But remember that f of x is just y. Okay, we're going to evaluate the function for each value of x. Okay, so we've got f of x is equal to 2 minus 3x. For this guy here, they're telling us that x should be negative 2. So all that's saying is that where you see x in the equation, you replace it with what? Yep, you replace it with a negative 2. That's it. So I'm going to replace this with a negative 2. Now I've got 2 minus 3 times a negative 2. And of course, that's a negative times a negative, so it's positive. So now you've got 2 plus 6, which I'm pretty sure is 8, right? So that means f of negative 2 is equal to 8. Okay, let's move on to the next one. Ooh, F word, fraction. We got this. So f of x is equal to 2 minus 3 of x. If we're trying to find f of negative 2/3, that means we're replacing the x value. Let me use my pencil actually. We're replacing the x value with a negative 2/3. Okay, and we're going to clean that up. So then that's going to give you 2 minus 3 times negative 2/3. And of course, these would go away, and a negative times a negative is a positive. So this simply just becomes 2 plus 2. Pretty sure 2 plus 2 is 4. So that means the function when x is replaced with a negative 2/3 is going to be 4. Boom. Last one. What the flying fig's going on here? There's a 2 on the outside? Whoa. Okay. So before we let that freak us out, let's solve for f of 1/6, excuse me. So if f of x again is 2 minus 3 of x, and we want to find when x is 1/6, all we do is we replace x with 1/6. That's it. No big deal. No stress. We clean that up. We get a 2 here. So now we've got, it looks like it's 2 minus 1/2. I'm pretty sure 2 minus 1/2 is actually 3/2. Okay, so what we were able to find is the fact that f of 1/6 is 3/2. Whoops. So what do you think the 2 does on the outside? Okay, well the 2 is just being multiplied by that value. That's it. Okay, so as we bring this down here, that's just simply 2 times 3/2. And I think we can all agree then that's just 3. Okay, so something that looked a little bit creepy with that 2 on the outside, all it was implying was multiplication. Okay, you've got 4 more to go. You got this. Okay. Oh, no, wait, I forgot number 9. Holy smokes. What value of x makes f of x equal to 0? That's a good question. So if f of x is equal to 2 minus 3x, we want to know when f of x would be 0. That's not x is equal to 0. That's actually meaning y is equal to 0. So if f of x was 0, what value of x would make that work? You're just replacing f of x with 0. This is awesome. I'm going to move it up a little bit. So maybe I bring the 3x over. So now I've got 3x is equal to 2. Ooh, that looked kind of weird when I did that. Sorry. Fiddle faddle foo. I'm running out of room. I apologize. So that's actually saying that 3x is equal to 2, divide by 3, divide by 3. So when x is 2/3, that function would be equal to 0. All right, now we've got 4 more. And now these are having our very, very spicy salsa dribbled on our carnitas burrito, our carne asada burrito. This is going to get really exciting because now we don't have just one function. We've got 2 different functions. One thing that students sometimes struggle with is they feel a function should just be f of x because the word function starts with a letter F. Makes sense to me. Okay, but a function can actually be represented with any type of letter. It can be F, it can be G, it could be H, it could be like M, it can be anything. So F is the most common, quite honestly, because function starts with F. G is also very common. These just mean 2 different functions. Think about them as 2 different vending machines. Think about them as 2 different boxes that you're throwing a value in and gets an output. Totally different functions. All right, let's do this. Find the following values, show all of your work. So this 4 on the outside, just means that if you can find f of 4, then that gets multiplied by 4. That's all it means. So let's find f of 4 first. Because we're using f, it refers us to this function here. So that's actually going to be x squared. So f of 4 is going to be 4 squared. Wait a minute. Does that mean 4 squared is 16? Yeah. Okay. So if this is 16, then all we're going to do, I might even put a little line right here, is we're going to take 4 times 16. Remember the 4 on the outside is just being multiplied by this function. So we're going to take 4 times 16, and that's just going to be 64. 64 is actually your final answer on that. 64 is your final answer on that. All right, 3 more to go. You got this. Okay. Holy smokeroonies. Am I seeing subtraction in this one? Yeah, and I'm seeing not only the function with F, but a function with G. Woo. Okay, start from middle and out. Let's focus just on this guy. Let's focus on G of 3. So G tells us we're going to use this function here. So I know that g of x is x minus 1. So if I want to find g of 3, all I'm doing is replacing x with the value of 3. So that's 3 minus 1. That's it. So g of 3 is actually equal to 2 because 3 minus 1 is 2. Uh-oh, we've got a 5 on, on the outside. Okay, so that's going to be meaning we're going to take 5 times this value. We already found this to be 2. So that's going to be 5 times 2, and I'm pretty sure that's 10. So what we were able to just find here is that this whole chunkaroo is 10. Okay, now I might do just a slight little squiggle, and now we're going to find f of 2. So the f function, again, refers to x squared. And if I want to find f of 2, then that's actually going to be 2 squared. Pretty sure that's equal to 4. All right, cool. So then we found that f of 2 is equal to 4. So really, this whole problem number 11 is just 10 minus 4, which I'm pretty sure is going to be 6. Okay, that's it. So just take it in parts, take it slow, and then you've got it. We're kind of inside and out. All right, we've got 12, we've got 13. We're almost done here. So same thing, work on the numerator first. F of negative 3 is telling me I need to focus on the f function. So since f of x is going to be x squared, then f of negative 3 is going to be negative 3 squared. It's not going to be a negative answer. Negative 3 times negative 3 is going to be a 9. Okay, so that's the top. Then we're going to work on the bottom. Ooh, they got fancy on us. They threw in a decimal. Ooh, scary. Nah, not for you guys. But that's telling us to focus on the g function. So if g of x is x minus 1, then g of 0.25 is the same as 0.25 minus 1. So when we think about that, I'm like, wait a minute, that's going to be a negative value. And I'm pretty sure that that's going to be negative 0.75. But maybe looking ahead, because I'm dealing with a whole number here and then I'm dealing with a decimal, 0.75 would actually be what as a fraction? Yeah, that'd be the same as negative 3/4, which in the end might make it a little easier. So I'm going to kind of do a side little bubble here. Holy smokes, I'm running out of room. But I want f of negative 3 divided by g of 0.25. Okay, so f of negative 3 was a 9, and g of 0.25 is a negative 3/4. So really what this becomes is 9 divided by negative 3/4. It's a complex fraction. So that's the same as 9 times negative 4 over 3. And I'm pretty sure, although I'm going to run out of room here, that that's going to be negative 12. And I might be a rebel and write it right on the bottom through that footer where it said student addition. I'm going to put a negative 12. Okay. So yeah, they can get a little harder, but you can handle it. Okay. Ooh, we've got fractions again. Fractions are our friends. Okay. So we want to find if f of x is going to be x squared, then f of 1/2 is actually going to be 1/2 times 1/2. So that's going to be 1/4. Sorry, my paper keeps moving there. I apologize because I'm at the end. And then let's actually find this guy. So to find g of x, because the letter g tells us which function to use, that's going to be x minus 1. So that's going to be 2/5 minus 1. So that's 2/5 minus 5 over 5, which is going to give us a negative 3 over 5. Cool. All right. All right, but we're not done. We're not done yet. And maybe I go, again, a nice little side bubble. Nice side cloud action, make it kind of fun. If we know that f of 1/2 is 1/4, and we're simply adding it to what g of 2/5 is, which is negative 3/5, we're just dealing with some good old fractions that we're going to add. So we need a common denominator. So that's going to be 5 over 20. My common denominator is 20, and that's going to be negative 12. And then, of course, 5 plus negative 12 is a negative 7. And negative 7 over 20 is your final answer. Okay, so this was lesson 7.1b, function notation.